Why are different CFD solver algorithms used in simulations? Imagine trying to solve a puzzle where each piece represents a different type of fluid flow. Some pieces are simple, others are complex, and each needs a different approach to fit perfectly. That's why in computational fluid dynamics, or CFD, we use various solver algorithms. These algorithms are like different tools in a toolbox, each designed for specific kinds of problems. When engineers work on designing turbines, cooling systems, or even aircraft, they need the right solver to get accurate results efficiently. CFD software relies on solving the Navier-Stokes equations, which describe how fluids move. These equations are complicated because they are nonlinear and involve many variables like velocity, pressure, and temperature. To make these equations manageable, the physical space where the fluid flows is divided into tiny pieces called a mesh. The solver then approximates the equations on each piece. But because each flow problem has its own quirks, one size does not fit all when it comes to solver algorithms. The main reason different algorithms are used is because of the nature of the problem itself. For example, steady flow problems, where the flow doesn't change over time, need different algorithms than in steady or time-dependent flows. If the flow involves gases moving at high speeds, the solver must handle compressibility, which adds another layer of complexity. Turbulent flows, which are chaotic and swirl around wildly, requiring special turbulence models and algorithms to capture their behavior accurately. Another key factor is how stable and fast the solver is. Some algorithms are very stable but take longer to reach a solution. Others are faster but might struggle with certain types of flows or mesh qualities. For example, pressure-velocity coupling algorithms like Simplec, and PSU are popular for incompressible flows, but each has its strengths and weaknesses in terms of speed and robustness. Computational efficiency also plays a big role. Large three-dimensional problems can involve millions of mesh points, so solvers that can handle this scale quickly are essential. Iterative methods like Krylov subspace solvers with preconditioning are often used because they can find solutions faster than direct methods, especially when dealing with huge systems. Multi-grid methods are another example, speeding up convergence by solving the problem at multiple levels of detail. The physics involved in the problem also determines the choice of solver. For example, if the simulation includes heat transfer, chemical reactions, or moving parts, the solver must be capable of handling these additional physics. The geometry complexity and mesh type also influence the choice. Structured meshes work well for simple shapes, but unstructured meshes are better for complex geometries, and some algorithms are optimized for one or the other. Commercial CFD software packages come with multiple solver options, each suited for different tasks. Engineers pick the solver based on what they need to analyze, balancing accuracy, speed, and available computing power. For instance, in designing turbines, they need solvers that can handle turbulent compressible flows with heat transfer to predict performance accurately. In building ventilation, steady-state solvers with robust pressure-velocity algorithms are used to model airflow and temperature distribution. For electronics cooling, transient solvers that can capture and steady heat transfer help in designing effective thermal management systems. In essence, no single solver can handle every fluid flow problem perfectly. Different algorithms are designed to tackle specific challenges, making the choice of solver a vital step in CFD simulations. Mechanical engineers select the best tool for each task to ensure they get reliable results without wasting time or resources.